Welcome to Spring LIB.
So here, we first need to take the sum of forces in the y direction. This is going to be equal to force normal minus force applied times sine of phi, and then minus mg cosine of phi. This is going to equal 0 because we have translational equilibrium in the y direction. We know that the sum of forces in the x direction will be rather, we can't say anything in the sum of forces in the x direction because it has acceleration in the x direction. So let's leave that for now and simply say that the force normal equals the force applied times sine of phi plus mg cosine of phi. So at this point, we can say that for part A, the angle measure equals 32 degrees, and this is between the force applied and displacement. So this simply means that the work done by the applied force would be equal to the magnitude of the applied force times the distance cosine of theta, and this is giving us 150 newtons times the distance of 5 meters times cosine of 32 degrees, and we have that the work done by the applied force is going to be equal to 636 joules. So this would be our answer for part A. And then for part B, they want us to find the work done by gravity. The measure of the angle equals 132 degrees between the force of gravity and the displacement. So we can say that the work done by gravity is going to be equal to the force of gravity times d cosine of theta, and this is equaling, of course, 18 kilograms times the acceleration due to gravity, 9.8 meters per second squared, times the displacement of 5 meters, and then cosine of 132 degrees. So the work done by gravity is going to be negative 467 joules. So this would be our answer for part B. And then for part C, we know that force normal is going to be perpendicular to displacement. So this means that the work done by the normal force is simply equal to 0 joules, because here cosine of 90 degrees would equal 0. And then lastly, for part D, we want to find the final velocity. So we can say that the work done by friction is equal to the frictional force times the distance cosine of theta. And this is going to equal the coefficient of kinetic friction times the applied force sine of phi plus mg cosine of phi times d cosine of theta. We know that this is going to equal -1, so we can say that here the work of friction is going to be equal to -0.10, the new coefficient of kinetic friction, times 150 newtons times sine of 32 degrees plus 18 kilograms, 9.8 meters per second squared, and then times, again, cosine of 32 degrees, close parentheses. And so this is going to equal, the work of friction is going to equal negative 114.5 joules. So essentially, just keep note of this number, because then in order to find the net work, it'll be the work applied plus the work of gravity. My apologies, work of gravity plus the work due to the normal force plus the work of friction. And this will be the change in kinetic energy. We know that this is going to be equal to 0. And this will equal 1/2 m times velocity final squared minus velocity initial squared. We know that the initial velocity is going to be 0. So essentially, here the velocity final will be equal to 2 times the work divided by m to the 1/2 power. And this is equaling 2 times 636 minus 467.4 minus 114.5 divided by the mass of 18 kilograms, all to the 1/2 power. And we find that the final velocity is going to be approximately 2.5 meters per second. So this would be our final answer for part D. That is the end of the solution. Thank you for watching.